Let's quickly go through some other techniques you might use in the process of feature engineering. One is called binning. The idea here is just to take your numerical data and transform it into categorical data by binning these values together based on ranges of values. So as an example, maybe I have the ages of people in my data set. I might put everyone in their 20s into one bucket, everyone in their 30s into another bucket, and so on and so forth. That would be an example of binning, where I'm just putting everyone in a given range into a certain category. So instead of saying that I'm going to train based on the fact that you're 22 and 3 months old, I'm just going to bucket you into the bin of 20-year-olds, right? So I've changed that number of 22 point whatever it is into a category of 20-somethings. So that's all binning is. Why would you want to do that? Well, there's a few reasons. One is that sometimes you have some uncertainty in your measurements. So maybe your measurements aren't exactly precise, and you're not actually adding any information by saying this person is 22.37 years old versus 22.38 years old. Maybe some people remembered the wrong birthday or something, or you asked them on different days and you got different values as a result. So binning is a way of covering up imprecision in your measurements. That's one way. That's one reason. Another reason might be that you just really want to use a model that works on categorical data instead of numerical data. That's kind of a questionable thing to be doing because you're basically throwing some information away by binning, right? So if you're doing that, you should think hard about why you're doing that. The only really legitimate reason to do this is if there is uncertainty or errors in your actual underlying measurements that you're trying to get rid of. There's also something called quantile binning that you should understand. The nice thing about quantile binning is that it categorizes your data by their place in the data distribution. So it ensures that every one of your bins has an equal number of samples within them. So with quantile binning, I make sure that I have my data distributed in such a way that I have the same number of samples in each resulting bin. Sometimes that's a useful thing to do. So remember, quantile binning will have even sizes in each bin. Another thing we might do is transforming our data, applying some sort of a function to our features to make it better suited for our algorithms. So, for example, if you have feature data that has an exponential trend within it, that might benefit from doing a logarithmic transform on it to make that data look more linear. That might help out your model in actually finding real trends in it. Sometimes models have difficulty with nonlinear data coming into it. A real-world example is YouTube. They published a paper on how their recommendations work, which is great reading, by the way. There's a reference to that in the slide here. They have a whole section on feature engineering there that you might find useful. And one thing they do is for any numeric feature X that they have, for example, how long has it been since you watched a video, they also feed in the square of that and the square root of it. And the idea there is that they can learn super and sublinear functions in the underlying data that way. So, they're not just throwing in raw values, they're also throwing in the square and the square root just to be careful and see if there actually are nonlinear trends there that they should be picking up on. They found that actually improved their results. So that's an example of transforming data. It's not necessarily replacing data with a transformation. Sometimes you're actually creating a new feature from transforming an existing one. That's what's going on here. So they're feeding in both the original feature X and X squared and the square root of X. You can see in this graph here why you might want to do that. So if I'm starting off with a function of X here on the green line, you can see that by taking the ln, the logarithm of that, I end up with a linear relationship instead, which might be easier for models to pick up on. I could also raise that to a higher power, which would actually make things worse in this case. But sometimes more data is better. Again, we're talking about the curse of dimensionality, so there is a limit to that. But that's what feature engineering is all about, trying to find that balance between having just enough information and too much information. Another very common thing you'll do while preparing your data is encoding, and you see this a lot in the world of deep learning. So a lot of times your model will require a very specific kind of input, and you have to transform your data and encode it into the format that your model requires. A very common example is called one-hot encoding. Okay, so make sure you understand how this works. The idea is that I create a bucket for every category that I have. And basically I have a 1 that represents that category exists and a 0 that represents that it's not that category. Let's look at this picture as an example. Let's say that I'm building a deep learning model that tries to do handwriting recognition on people drawing the numbers 0 through 9. This is a very common example that we'll look at more later. So to one-hot encode this information, I know that this thing represents the number 8. And to represent that in a one-hot encoded manner, Basically, I have 10 different buckets for every possible digit that might represent 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now, I usually start counting at 0 here, so you can see here that in the 9th slot there's a 1 that represents the number 8, and every other slot there has a 0 representing that it is not that category. That's all one hot encoding is. So again, if I had a 1 in that first slot, that would represent the number 0. If I had a 1 in the second slot, that would represent the number 1, and so on and so forth. We do this because in deep learning, neurons generally are either on or off. They're activated or they're not activated. So I can't just feed in the number 8 or the number 1 into an input neuron and expect it to work. That's not how these things operate. Instead, I need to have this one hot encoding scheme where every single training value, that label, is actually going to be fed into 10 different input neurons, where only one of them represents the actual category I have. We can also talk about scaling and normalizing your data. Again, pretty much every model requires this as well. A lot of models prefer their feature data to be normally distributed around 0, and this is also true of most deep learning and neural networks. And at a minimum, most models will require that your feature data is at least scaled to comparable values. I mean, there are models out there that don't care so much, such as decision trees, but most of them will be sensitive to the scale of your input data. Otherwise, if you have features that have larger magnitudes, they'll end up having more weight on your model than they should. Going back to the example of people, if I'm trying to train a system based on their income, which might be some very large number like, 50,000, and also their age, which is a relatively small number like, 30 or 40, if I weren't normalizing that data down to comparable ranges before training on it, that income would have a much higher impact on the model than their ages. And that's going to result in a model that doesn't do a very good job. Now, it's very easy to do this, especially with scikit-learn in Python. It has a preprocessor module that helps you out with this sort of a thing. It has something called min-max scaler that will do it for you very easily. The only thing is you have to remember to scale your results back up if what you're predicting is not just categories and actual numeric data. So sometimes if you're predicting something, you have to make sure to reapply that scaling in reverse to actually get a meaningful result out of your model at the end of the day. Finally, we will talk about shuffling. A lot of algorithms benefit from shuffling your training data. Otherwise, sometimes there's sort of a residual signal in your training data resulting from the order in which that data was collected. So you want to make sure you're eliminating any byproducts of like how the data was actually collected by shuffling it and just randomizing the order that's fed into your model. So often that makes a difference in the quality as well. There are a lot of stories I've seen where someone got a really bad result out of their machine learning model, but by just shuffling the input, things got a lot better. So don't forget to do that as well. And that's the world of feature engineering in a nutshell.